Hello, everyone, and welcome to this ISCARSAH webinar on earthquakes and traditional construction. My name is Tim Michiels, and I am a structural engineer at Old Structures Engineering in New York and adjunct professor of historic preservation at Columbia University. Today's webinar is brought to you by ISCARSAH, or the International Scientific Committee on the Analysis and Restoration of Structures of Architectural Heritage. As several of you might not be familiar with ISCARSAH, I will briefly introduce our scientific committee before we get started with the webinar. We are an international group of engineers, architects, scientists, and educators dedicated to the restoration and care of built heritage. We mostly focus on the structural and technical aspects of conservation and architectural heritage. We have an elected board. Many of whom are here with us today. Our president, Gorun Arun, will be our first speaker. Our Secretary General, Tom Morrison, is as always working hard behind the scenes, letting people into the meeting room, monitoring the chat, and so on. The goals of ISCARSAH are, amongst others, to disseminate knowledge, promote international cooperation, and organize international training programs. Another goal is to collaborate with other scientific committees. So we are very glad today that we have speakers who are also active in ISCAIA, the International Scientific Committee that works on urban heritage from ICOMOS, and ICORP, which works on risk preparedness for this webinar. In the past years, ISCARSAH has published principles for the analysis, conservation, and structural restoration of architectural heritage. We publish newsletters as well. Currently, we are developing guidelines for the analysis and restoration of structures of architectural heritage. And before the pandemic, we were organizing yearly workshops. The latest ones were in Korea, like this one, Turkey. Here's some pictures of that workshop. And then the very last one was in October 2018 and was held in Iran. We look forward to continue this once the pandemic is over. You can reach us at the following email that is coming up when my slides pick up. There we go. iscarsah@gmail.com. You can follow us on Facebook as well, or you can find us on our website. Okay, that brings us to our webinar on traditional construction and earthquakes. We wanted to highlight traditional structures made from, for example, wood, masonry, or earth in seismic areas, because these buildings are often seen as the most vulnerable to earthquakes. Yet often, these buildings have seismic mitigation strategies built in as part of their original construction or past repair. All too often, unfortunately, this built-in knowledge has been lost or is misunderstood. As the safekeepers of old buildings in earthquake areas, we all grapple with similar questions. How do we balance, on the one hand, the life safety of all the users of a building and our desire to preserve that building for future generations? And on the other hand, how do we implement a minimum intervention that is the least intrusive to that same building? Sometimes engineering solutions take a conservative approach that try to maximize structural strength, yet they go well beyond what is actually needed to ensure life safety. Often, this damages valuable elements of the building, and those well-meaning interventions might paradoxically, in the end, contribute to a building's destruction. Additionally, the regulatory framework provided by building codes to deal with traditional buildings is often lacking. Therefore, we need to study, learn, and discuss traditional architecture. Building technology in seismic regions has evolved over centuries and has developed what is referred to as a local seismic culture. Today, we have 5 distinguished speakers from 5 distinct regions around the world who will discuss their local seismic culture. We also hope to hear from you. We look forward to taking your questions after the presentations. Feel free to post them in the Zoom chat window at any time. We would also like you to consider presenting on your own work on traditional construction in a follow-up webinar, probably held at the end of March. A call for presentations will be distributed shortly. Before handing over the floor to our speakers, I would like to thank Evan Spear and Tom Morrison, who are my co-hosts today and who are managing the webinar logistics behind the scenes. I would also like to thank the other members of the organizing webinar committee, Steve Kelly, Kai Weisse, Gorun Arun, Grigor Angeliou, Chola Akintunde, Stacy Vallis, and Maya Segara Lagunes. Finally, I would like to thank all of our distinguished speakers for agreeing to share with us their work. So then without further ado, I would like to introduce you to our first speaker, Professor Gorun Arun, who is also our president of ISCARSAH. She is full professor and dean of the Faculty of Fine Arts and Architecture at Hasan Kalyoncu University in Gaziantep, Turkey. Her research focuses on diagnosing the structural problems of existing structures, including buildings made of masonry, timber, early concrete, and steel located in seismic areas. She has led 12 national and international research projects on historical structures, authored 5 books, and written more than 200 scientific papers and reports on heritage. Welcome, Madam President. You have the floor.
Thank you. Okay, shall I share my screen?
Yes, please.
Okay. Good morning, good afternoon, and good evening for all of you. I'd like to thank all of you participating from different countries for being here with us. This pandemic period kept us from meeting face to face and to share our experience and enjoy spending time together. But the constraints of this period also enforced us to use digital communication. I hope this webinar will serve to increase synergy among us. Now I will present my topic is traditional earthquake mitigation measures in Anatolia. This presentation is consisted of construction methods of master builders from various civilizations lived in Anatolia. It is based on experience made during diagnosis phase of restoration works and reviewing archaeological and history of architect publication. For those who don't know the place, Anatolia is far west peninsula of Asia. Okay. Earthquake was and still is one of the most threatening actions to buildings in Anatolia. As you see here, vernacular or monumental, most of the heritage structures are an earthquake area. In Anatolia, main construction technology till mid-20th century was timber and masonry. Above you see the different types of timber structures, and below you see different types of masonry structures. In most places, due to the scarcity of wood, masonry structures were built, and most of heritage, historical heritage survived up to date are masonry construction. The master builders of the past designed their, when designing their building, they were responsible for every aspect. They had to assume the roles of architect, civil structural engineer, mechanical engineer, as well as the city planner and the contractor. Today, we say earthquake resistant design is necessary in order to make the building safe. And in earthquake resistant design, it is suggested to maximize the energy absorption capacity of the structure and minimize seismic action. To maximize energy absorption capacity of the structure, energy dissipation has to be provided, redundancy has to be provided, and geometrical irregularities has to be avoided. To minimize seismic action, building has to be light, weakening effects on the building has to be avoided, and amplification of ground acceleration has to be minimized. Building masters use techniques developed from previous cultures, their own trial and error, and techniques transferred from one generation to another They were able to size and design their buildings, taking proper account of the environmental conditions. Let's see how these demands are met by our master builders. To dissipate energy, the masonry structures withstand lateral loads with compressive strength of its material, friction between the units, the movement of the units. The movement of the units is important to disperse energy. In connecting stone units with each other, they placed metal connectors in lead, which is very soft material, so that it lets the units move under lateral loads to disperse energy. If they are using a mortar to connect the units, then they used weak rather than strong mortar, so that it can slide, the units can slide under lateral loads during the bed joints and dissipate energy. Repair of the mortar is not so hard, but it keeps the main structural units. Redundancy has to be provided. Redundancy of the structure depends on the nature of the structural system and detailing of its elements. But masonry structures are inherently redundant structures. Building masters knew the physical dimensions of height to thickness ratio and length to thickness ratio of the wall are important factors in seismic performance of masonry walls. They provided horizontal lacings that tied the outer faces of the walls. This prevents wall bulging under gravity loads and reduces the slenderness ratio of the wall. These lacings could be brick and stone, or metal in stone walls, timber in brick, stone, or other walls. They provided vertical supports at certain intervals to the long walls. These could be cross walls and intersecting walls, or vertical ties or of timber or stone buttresses. To avoid geometrical irregularities as long projecting and different weighing components of a building, buildings were separated as seismic joints. Here, the building parts staying side by side were separated by not joining the masonry units to each other. The foundations were also separated. To minimize earthquake effect, building has to be light. But masonry is heavy construction. The only way to reduce the weight of the structure was to make light roof and floors. In places where there's no wood, masonry walls and domes were built to span the plan areas. The building masters, knowing the geometry and behavior of the walls and domes, they used clay pipes in the area of compression to reduce the weight. To construct a flat roof over these domes or walls, between the flat roof or floor and the wall, they emptied the space in between or used clay pipes or amphora to reduce the weight of the building. Again, to make the building lighter, in multi-story buildings, in seismic areas, were constructed getting gradually lighter at the upper floors, both with material and the thickness of the wall. This, for example, when we look at this, the 3-floor building, ground floor is masonry, second floor is timber with brick infill, second floor is badadi. That means the frame, timber frame left empty inside. In the middle, the ground floor is masonry. First floor, the masonry, but the inner walls are timber. Second floor is totally timber. Here, the ground floor is masonry. The first floor is masonry, but inner walls are timber. This way, the building gets lighter at upper floors, and the center of gravity of the entire structure is brought closer to grade to meet the seismic demands. To avoid weakening effects, of course, water is a non-seismic threat to all kinds of buildings, timber or masonry. Depending on the porosity of the foundation construction material and soil characteristics, it can damage the wall and soil, eroding away portions, and by reducing the strength. And moisture in building causes loss of material and weaken the structure in long term. So water drainage was given high priority during its design and construction. To prevent instability of the building from underground water movement seasonally or daily, and to collect the surface water of rainfall, they designed an effective drainage system. The major components of this drainage system was wells or cistern in the basement of the building, galleries or channels to discharge the water out of the building, and gates for ventilation. Because this application is forgotten, when a new construction has to be built beside an old masonry or timber construction, it breaks the discharging system. Then the water starts to race to the building, weakening the material and softening the soil, so that leads to the foundation settlement of the building. To minimize amplification of ground acceleration, of course, it has to do with the design of the foundation. Usually, the soft soil was consolidated by timber piles. The timber piles were tied by a timber mesh embedded in porous mortar. The foundation walls rested on this platform. The foundations of masonry or timber building was of masonry. The thick foundations were generally a vertical wall in the soil. As the wall thicknesses became thinner, the foundation walls widened at the foot. If the wall was composed of closely spaced piers, then and there is no sufficient depth to step the foundation, an inverted arch or vault were made. Master builders knew that the acceleration generated by ground displacement is amplified or attenuated by soil structure. In high seismic zones, the building masters introduced special techniques in foundation construction to provide lateral stability. If the rock bed or hard soil was deep, the foundation walls rested on a low layer of sand, gravel, or small stones. In masonry village houses in Anatolia, were constructed over a layer of approximately 40 centimeter sand till 1960s. That's when the reinforced concrete became popular in villages also. If the rock bed was close to the surface, a flexible base was provided by placing single or more layers of wood foundation at the foundation base. The foundation walls of the buildings in and Üsküdar, you see, are rested in grillage. Here, in the project of inverted vault foundation of Edirne Kapı Cistern from 19th century, You can see the timber grillage at the bottom. So this foundation is resting on 2 layers of timber grillage. If the rock bed was on the surface, the rock was carved in the form of trough so that each stone of the foundation wall could be placed in the rock as if resting in a cradle. Here, the big dressed stones of the wall rested on high edges of the trough, not inside. The space in between was filled with briar, pieces of coal, or animal skin to reduce the friction. At the bottom, you see Malabadi Bridge on southeast of Turkey. The piers of Malabadi Bridge rests on a lead layer. A different foundation system practice was found during the octagonal tomb. Around this octagonal tomb, 6 meter high, 2 meter thick wall at a 4 meter distance to the tomb was found, and it was the shape of the octagonal. This is as if octagonal and hexagonal forms are not adequate forms for earthquake areas. So this buried wall acted as a retaining wall to absorb the first shock of earthquake forces, and there is no damage in this octagonal tomb. Another obelisk. It was erected in during Byzantine period at the Hippodrome. This obelisk experienced many severe earthquakes in its lifetime, but had no damage. When we look at it closely, the obelisk is placed 3 centimeters each side. This rests on a cubic marble, 3 meters each side. And this cubic marble rests on another marble platform, 4 to 3 meters high. And at the corners, there are granite, cubic granite stones with rounded edges. Could these granites be seismic isolators of Byzantine era? Okay. Okay, to conclude from previous cultures, their trial and error and transfer of knowledge from generation to generation, were able to size and design their structures. They connected masonry units properly so that they disperse energy, provided seismic joints, but by not connecting the different weighing components of a building. They had knowledge on geometry and behavior of structural elements. They used lighter construction material on upper floors to hold the center of gravity of the building close to grade. They designed an effective underground and surface water drainage system. In earthquake areas, changed the natural frequency of soil or provided flexible base. Okay, thank you. This is my presentation, and I'll give you some reference which I used to interpret what I have seen, what I have met during the diagnosis phases, to understand why these were constructed that way. These references really helped me a lot. You see, the oldest one is from 1570, and the young ones are the archaeological excavation reports. Thank you.
Thank you so much for that wonderful presentation, Professor Arun. We will move on. I will also just repeat for the people who just joined, welcome. You can ask questions in the chat. If you have questions for Professor Arun, you can post them in the chat now. We will come back to them later after all of the presentations. Right now, we will move on to the next presentation, which is by Kai Weisse from Nepal. Kai Weisse is a Nepali of Swiss origin who studied architecture in Zurich. He is presently president of ICOMOS Nepal and has been involved with management of World Heritage properties in Asia for the past 2 decades. Since the 2015 earthquake in Nepal and the 2016 earthquake in Myanmar, Kai has been involved in post-disaster rehabilitation, including the restoration and reconstruction of historical monuments. Welcome, Kai.
Good evening from Kathmandu. Let me share. So good evening from Kathmandu. My presentation is on rebuilding Kastamandap, the challenge of using traditional technology. On the image, one sees the actual protagonists of this project. We have the Member of Parliament, Rajesh Sakya, who is actually sort of the responsible to deal with the political aspects. And then we have the 2 main artisans. On the left, we have the main carpenter, and to the right, our head mason. And here you see they're carrying out one of the many rituals that is part of this reconstruction process. Just a very short introduction, of course, to the earthquakes that take place along the Himalayas and the ones that have affected the Kathmandu Valley. The most recent one was, of course, the 2015 Gorkha earthquake, which was 7.8 magnitude. And previously, we had the 1934 Nepal-Bihar earthquake of 8.4 magnitude. So we see that sort of every 80 to 100 years, we have a large earthquake impacting the Kathmandu Valley. The case study is this Kastamandap, which you see an image on the left, which did not collapse during the 8.4 magnitude 1934 Great Bihar Nepal earthquake. There were major restorations that took place in 1966, followed by repairs in 1972 and 84, and probably in between several other sort of repairs and work were carried out to this monument. And but the Kastamandap collapsed during the recent 2015 Gorkha earthquake of magnitude 7.8. So the question is, why did it collapse during this earthquake, and why did it actually survive the previous earthquake? And this was sort of been one of the big questions that keep arising, and we're still struggling to actually understand, try to deal with this question. The sad situation was that when it collapsed, there was blood donation going on, and quite a lot of people died. So it was a very traumatic experience. The Kastamandap is a pavilion, a timber pavilion, but we also have a bit of brickwork around the core, which sort of complicates the entire structure, trying to understand its structural character. And the importance of this structure is that it gave Kathmandu its name. So Kathmandu is the timber structure or monument or pavilion. And so Kathmandu was named after this monument. So it, of course, has a major significance. And once it collapsed, it became quite sort of a politicized issue. Now, the initial sort of structural assessment that was done and the original design that was prepared came up with a whole series of recommendations, which are sort of very standard recommendations that are made for all our monuments in the Kathmandu Valley. The roofs have a thick layer of mud, which the tiles are stuck into. So the question was that it was too heavy and we needed to reduce the load on the roof. Another point is that there wasn't sufficient stiffness, and the traditional monuments don't have any diagonal bracing, and the floor, not even on the floor. So the question was how to introduce this diagonal bracing to provide a certain stiffness to the building. The timber joints are inadequate. So the question was, how do we strengthen these joints using various, like metal brackets and additional interventions. Then the question of the brickwork not being reinforced. So in this monument, we actually really have brick and mud mortar with no sort of reinforcement. So the question was how to introduce sort of horizontal vertical ties. Then we had sort of the mud mortar not being strong. So we needed a stronger mortar or the use of additives. The question also arose of having some kind of a plinth level tie beam, which the suggestion was to use concrete. And the question of the foundations not being sufficient and that we needed to have some kind of micropiling done. However, all these suggestions were not accepted. So this sort of activist-led community protests wanted the monument to be rebuilt as it was. The question, of course, arises what that means. But the point was that they did not want these sort of foreign interventions introduced to this monument. And this actually led to the reconstruction being halted for 3 years. And only in 2018 could we actually begin the reconstruction, of course, taking into account that we needed to rebuild it as it was. Now that was, of course, brought up a lot of questions. During these 3 years, we were actually able to do a lot of research, which was, again, good in a certain sense. There was archaeologists, actually from Durham University, excavated into the foundations. And we found that the foundations were, the brick and mud mortar were in perfect condition. However, a lot of the timber joints and the timber had deteriorated, and especially the link between the main timber posts. And here in this image, one sees the keystones where the main 4 posts were supported by the keystone. And one of the 4 stones was actually missing. So probably somewhere in between, the deteriorated timber was just sort of cut at the bottom, and the flooring was sort of shoved underneath one of the 4 main central posts, which means that structure was actually standing on 3 of its main central posts. And sort of these are the kind of things we found, that it was actually these kind of interventions that would have been probably one of the main causes for the collapse of the structure. We also found through dating that the brick foundations were the oldest part from the 7th century, which was actually 100 years older than what we thought it was. We had the main timber structure from the 11th century, and we even found the sort of the oldest timber bracket, which was from the 5th century that had been reused in the structure. So starting with the reconstruction, again, the task was to rebuild it as it was using traditional technology, materials, know-how, and of course, this also was linked to traditional sort of rituals. And here on the left, one sees the Vajrayana priest carrying out a ritual, and also including the blessing of the artisan's tools. With starting with the foundation, the brickwork, we found that the bricks were very specifically, there was a specific scale to the bricks, the size, but also that the foundations had smaller foundations were 8 courses in 3 levels, and the deeper foundations were 12 courses each in 3 levels, which meant that all the proportions had to also be considered when we started reconstruction, which meant ordering bricks of the specific size that we required. Here we see our head mason working on trying to get the right mud mortar consistency. So we actually had to sort of develop, the understanding of the brickwork and the mortar to use in this monument. Now, already in the beginning, when we removed the rubble, we saw that the plinth was actually sort of wavy, which meant there must have been some kind of settlement. But looking at it more specifically, we realized that, of course, there wasn't any settlement. Foundations were in perfect condition, but actually there was uplift in the areas where we did not have a structure sitting on top. So wherever we had a wall or a post, it actually confined the masonry, while the areas in between there was uplift. So this is actually quite a different sort of a response or effect on the brickwork, which was, again, we had to remove about 4 or 5 courses and relay the plinth so that we could bring it to a proper level. The other big issue was, of course, getting the artisans who could work with the timber, which was, of course, the main part of this structure. And luckily, we have the artisans. And to some degree, we could reuse the timber elements, but a lot of it we had to replace or use the old timber and reuse it. But luckily, again, with the knowledge of the artisans, it was possible to carry out this work. On the right, we see the bamboo scaffolding. Now, it of course looks very traditional and it looked very good, but it was actually also very practical because it was much more flexible than the using pipe trusses. And it was to pull up the timber elements, it was possible to do it by hand, meaning using ropes and human power and not use any heavy machinery, which then also allowed the sort of communities to participate in the process and help carry these timber elements to the site. Now, with the timber, again, we have, I was told over 150 different joints. We still need to do further research on this. So supposedly a lot of these traditional joints have already been forgotten. We're hoping to actually get the artisans that are still around to help us document these joints. The main characteristics is, of course, that it's fully timber joint, where we have sort of pegs holding the different pieces together. And this has been, of course, part of this adaptation to the seismic requirements of the structure, where certain movement is allowed, and it sort of holds the structure together. The problem we actually faced was with the brickwork, where in the foundations we of course found the brickwork in perfect condition, but in the superstructure there was a lot of damage which was there possibly even before the earthquake, but then of course after the collapse a large part of there was additional damage to the brickwork. And there was a lot of discussions on how to deal with this. And of course, the question was of how to ensure that the brick components of the monument were better reinforced. This is a big discussion, and I've discussed this with many people, including Arun Menon and also Randolph. I spent many hours discussing with him. Hopefully he's also listening in on this because I've used his images. The traditional monuments in Kathmandu actually have horizontal timber lacing, but very often they don't use vertical elements. So it's actually really just a horizontal timber lacing holding the structure together. On the other hand, which is again sort of similar to the construction in Kashmir, the Tak construction, we have, of course, the other possibility of timber framing, which is found in many parts of the world, and also the example in Kashmir. But this is not used very often in Kathmandu. We have found it in a few places where either the structure, like for example, in the 9-story palace, where the structure has been much larger than traditionally built, where sort of vertical elements have been introduced into the brickwork, but this is actually not commonly used. What we actually saw also in Bagan was the whole question of confinement of brick masonry. And here sort of steel caging around the brickwork was very effective. Again, the question here is, how do we ensure sort of this confinement or reinforcement of brick masonry in mud mortar? That's again, I've raised a lot of questions and we haven't really come to detailed conclusions on this. I think it still requires a lot of research. What we ended up doing in the Kastamandap was sort of introducing a very minimum timber sort of reinforcement into the brickwork, sort of to ensure that there is some form of confinement, but keeping it to a minimum, that it doesn't really take over the function of sort of a, sort of a timber framing with the infill. And this was really to ensure that the brickwork is able to take on a certain level of stress. This is the present status of the Kastamandap. We're just about completed the main structure. We're still waiting for timber to be provided for the remaining roof structure. What we're working on is also a continuity plan, since we know that one of the main causes for the collapse was the lack of maintenance and sort of the requirement of managing the structure over time. We are working on a continuity plan, which includes sort of the maintenance and monitoring of the structure. We're hoping to put in sensors as well and do structural monitoring, but also that we manage the use of the monument. And the continuity also includes here on the lower image, we see one of the brackets, and this is actually from the 5th century. So there's a continuity also in respect to material. As a conclusion, it's always this question of how do we deal with sort of the traditional technology, materials, and here sort of bringing the scientist. Here is Professor Ian Simpson from Stirling University taking a sample of the timber while our head carpenter watches. He looks very skeptical. But on the right side, we've managed to get him to try out the resistometer. Traditionally, of course, you just knock on the wood and you know how, whether it's good or not just by listening to it. But again, the question is, how do we bring this traditional knowledge and modern technology to actually communicate with each other to be able to deal with these monuments? We're actually planning our inauguration on the 25th of April this year. It would be the 6 years after the earthquake and 3 years after we started construction, but we're not quite sure whether we'll manage to complete it by then. We're still hoping to do so. Thank you very much.
Thank you so much for that wonderful presentation from Nepal, Kai. Just a reminder to everyone, keep the questions going in the chat. We've gotten a great set already, and we will discuss them after the 5 presentation. We will now move on to our 3rd presentation, which will be by Grigor Angeliou. He is an assistant professor of structural mechanics at the Department of Civil and Environmental Engineering at the Politecnico di Milano. His research focuses on the application of modern technologies for an improved diagnosis of the structural safety of historic buildings related to earthquakes, aging, or soil settlements. This includes a combined application of the finite element method, parametric modeling, LiDAR scanning, and structural health monitoring. Welcome, Grigor. The floor is yours.
Thank you, Tim. Okay. Sorry, can you see my screen?
Yes, we can.
Okay, thank you. Thank you everybody for attending this seminar. I will be talking today about the earthquake of November the 26th in Albania. So I will be talking about the post-disaster damage assessment of historical buildings. About the content of the presentation, I will discuss a bit on the typologies of historical building in the earthquake region. Just go very briefly on the shape map of the November 26th event. I will present some damage survey statistics on the earthquake area. Then I will prefer here to discuss 3 case studies, which in my opinion are the most significant ones. And then I think that is very interesting also for the audience here to go, let's say, through a detailed structure assessment in one of the case studies, the Tower C in the Castle of Durrës in Albania. And then I would like to draw, of course, some conclusions with regards to the earthquake, historic buildings, and the strategy for the reinforcement and the rebuild. So because of, let's say, the big audience here, from all the world, Albania is located in the Balkan region, just beside Italy and Greece. So it's a territory characterized by moderate seismic events. Here I'm just plotting a map, from the US Geological Survey, and you can see here some of the events with a magnitude of 5.5, since January 2019. So, I mean, there are continuously, let's say, important earthquakes. The majority of the earthquakes that we have in the country is characterized by low to moderate intensities, usually less than 7 Richter, and rarely with high intensities, even with a magnitude more than 7. It is important also to see what are, let's say, the types of buildings that we have in the region of the earthquake. Now, there are different types of buildings. We have cult buildings related to Muslim or to Christian religion. Here you can see, for example, the Tekke of Dolma, which was damaged during the earthquakes. We have vernacular architecture from the 18th or 19th century. This is an example. This is the Ethnographic Museum of Korea. We have engineering infrastructure as bridges, aqueducts. Here, for example, is the Uratabago, one of the bridges in Tirana. but we have also castles, as this is the castle of Leja, for example. There are many fortifications in the area, but we have also what we call design buildings. So these are mostly of the 20th century. For example, this is a building of the 20s and 30s. Here you can see some of the number of buildings. I would like to state here that when I'm talking about historic buildings, I'm mostly focused here on designated historic buildings. So it means that we could have more historic buildings, but these are the designated historic buildings according to the Albanian law on cultural heritage. And you can see here some of the numbers. Now, with regards to the earthquake, most of the buildings, so the majority of them, were located, of course, in the region of Durrës, the region of Tirana, and the region of Leja. Of course, there are also examples of damages in the other regions, as Elbasan or Shkodër, but that is not the majority of the cases. With regards to the earthquake, which was very devastating, of November 26, 2019, here you can see the shake map, where you can see that the earthquake was pretty severe, you know, in the region close to Durrës, and then quite strong, you know, in the other regions. So, for example, close to the capital in Tirana, where we have a very high density of buildings, in Kruja, or also in Leja, which is located here. So, in this region, we have very devastating effects. Of course, here I would stop in the case of discuss the case of historic buildings. Now, there was also a very interesting thing which has to be discussed, in my opinion, that before the earthquake of November 26, we had also another earthquake in September 21st. So just 2 months before that, you know, with a magnitude lower in terms of magnitude, but still which provoked damage in the buildings. Of course, not so heavy as the last one, but I mean, the word damage, and probably, you know, just the 2 months period did not allow for a proper survey and proper repair of this damage in many buildings, not only just the historic one. So this is a very interesting point which has to be underlined here. Here you can note the 3 regions, you know, of the earthquake. This is the epicenter. And these are some data collected by the National Institute of Cultural Heritage on a stock of 110 designated buildings. So on a stock of 110 designated buildings, 10% was like previously damaged. And then we had more or less 40% with negligible damage, 25–26% with moderate damage, and more or less 22–23% with very severe damage. So this is on the stock of 110 buildings. It is very interesting to see because, I mean, from that point, then we can also generalize about the damage that the earthquake caused in buildings in the country. So these were some general statistics about the earthquake. I think it's good for us now to focus on some of the cases. Now, I have chosen 3 cases belonging to the same, let's say, structure topology, towers, because I think that these are the 3 most significant ones, but are also kind of communicative, so also easily to understand, but also to make comparison between them. So I will be discussing the Tower of Kruja, located here, the Tower of Preza, and the Tower C in Durrës. of the Dures fortification. So we start from the one, let's say, which is a bit more far from the epicenter, and more or less we go closer. Of course, each of these examples has, let's say, its own characteristics and specifics. This is the Tower of Preza. You can see on the left an image of the tower before the damage. This is an image of 2013. And you can see on the right and an image after the damage of 2019. So the complete upper part of the tower had collapsed. It is very important in this example to see the presence of pre-existing cracks. So you can see clearly here, I did not try to highlight anything because in my opinion is pretty evident that you can see, the presence of the cracks, already in 2013. And the same one, of course, after the earthquake got magnified, but it looks like, there were, let's say, an important factor in the part of the collapse. Something very interesting here was an addition, recently, but more or less like 2 years before the collapse. And you can see that the lower part of the construction, which had the insertion of some steel ties, resisted pretty well. What is more important here is the other part of the tower. So you can see again another image from before and after. And again, in this area here, you can see already, the presence of the cracks. So again, it is shown here how the importance of the presence of these pre-existing cracks, it is very important in the structural behavior of the earthquake. So I would like to highlight here the importance of the survey, already on site. Now I would like to pass to the second case study. This is the Tower of Kuya. Of course, this is a much bigger tower compared to the previous one. But again, beside the specifics of each case, I would like to draw here a comparison between the first and this one, in the sense that, the part of the colonnade in the upper part, in this case, did not collapse. If you make a comparison between this one and this other one. And the reason it was because, this one here was basically rebuilt in concrete during the 70s or the 80s, more or less. And in the zoomed part of this, you can see here the reinforced concrete beam on the base of it, which basically during the earthquake more or less floated, in this soft layer of mortar. So it's some kind of base isolation at the end. But another important aspect here is, to make a comparison between this facade and this other one here. So this part of the facade and this other one. The importance is in the fact that in this part of the facade, the damage was more or less pretty limited. But on this one, you see that, the damage is pretty important. So if we analyze then more in detail the part of the technology of construction, you can see clearly here that we have timber ties more or less placed regularly, one every a meter or a meter and a half. So these are the two edges of the tower, basically. And it is demonstrated here quite easily that this traditional technology of timber ties, it's a good one, in helping to prevent seismic damage. Of course, there is some damage, but it's much more limited compared to the other facade of the building. So this is an example of how, when the existing anti-seismic system exists in the building, it works. This is another example of another tower. This is in the city of Durrës. So also here we have a local collapse, so a big portion of one of the towers, this is the tower C, collapsed. What is very interesting in this case is that we have also, two other towers with the same geometry, just let's say like 20 meters, from this side and 20 meters from the other side. And the two of them did not collapse, but just this one has this local collapse. I would now show in detail, some of the structure assessment procedure that we performed in this case in order to analyze this case study. I think that that would be also interesting for the audience here. This part is divided mainly in two parts. One is the data collection and analysis, and then is the structure analysis procedure. The idea behind all of this is to have, let's say, certain proof, certain scientific proof on the causes of the collapse. And this, of course, will help in the restoration approach. So you can see on on the left side of the screen, photogrammetric survey of the tower. The tower was built by the Byzantine Emperor Anastasius I in the late 5th century. Then it had, during the earthquake of 2073, there was collapses, in the whole city walls, and part of the tower was damaged or collapsed. This one that you can see here, and then there was, let's say, a major reconstruction process of the city walls. And after that, we have another late phase during the Ottoman Empire, which is this one sign here. This research is according to Professor Gerard Karaiskai, who is a noted scholar for the analysis of the fortification in Albania. This is a geometry of the tower. And during the structure survey, we noted, let's say, some weaknesses in the tower. The first one, first of all, this is the block which collapsed. This is a huge one, actually. And we noted, let's say, the first weak plane, which is this one here. There was a second one, this one here, which is also, as you can see, is pretty much flat and is connected also with one of the phases of construction. But another very interesting discovery was this cavity, this void at the base of, more or less at the base of this activated block. So we had to be certain which was the main cause of this collapse. Finally, we performed also analysis on materials. And in conclusion, I mean, the mechanical properties here were pretty good. Another part is, which we discussed, was the part of the seismication. These are some accelerograms which we recorded in the city of Durrës. This was recorded from the Durrës station, but unfortunately, we have just 15 seconds of the registration. So all the calculations there are performed just with these numbers finally. With regards to the spectral acceleration, It was very interesting in this case to make a comparison between the earthquake spectrum and the one suggested by the design code. And it was noted that it was more or less, the spectrum of the earthquake, more or less what was suggested by the design code. So it confirmed, let's say, on the strongness of the earthquake finally. Here you can see, if you would like to go into more detail, also a comparison between the one in blue and the one in black, between the earthquake of November 26 and the one of September 21st. So, we had two quite strong earthquakes, although, the first one was not felt that much, did not have that much damage, compared to the second. Here we can see a finite element, a model of the tower, in order to study much more in details and assure on the causes of the collapse. This is the model analysis. It was interesting, without stopping here in much detail, to observe, here some similarity between the collapse and some of the modes in the numerical model. We analyzed the effect of the soil settlements, and what came out was that one of the major cracks, this one here, or one of the, let's say, important weak planes that we saw there, could have been related very strongly to soil settlements. So in some kind of way, this somehow excluded, the first weak plane as one of the causes of the collapse. In order to have also some, more simple analysis, were performed here by also limit analysis. The result of this analysis showed that, these were the kinematic multipliers, and the results showed here that the failure, in this direction would have been, let's say, the first one. So it kind of, let's say, highlighted that, the surface here, which was very flat and did not provide any friction, would have been one of the major causes of the collapse. While, the weak plane one here could not have been, let's say, the major one for the collapse because of, if we calculate here the multiplier, with the friction, the safety would have been pretty high. In order to give to this, the final assurance, on the collapse, we performed some time history analysis with the actual accelerogram, and you can see here that at the simulation time of more or less 12 seconds, you can see the formation of damage at the beginning in this area, close to the construction joint, where we have a very flat surface, in the masonry, so no friction, to guarantee the continuity of the structure. And then after some time, we see also, some development of the damage close to where we have actually the cavity in the model. So at the end, this kind of confirmed that, the damage arises firstly at the point where we have this construction joint, and then, develops through the part of the cavity, confirming these 2 points, as the most important factors, to cause actually the collapse. So this is one last simulation to show, how the collapse happened. And you can make here a comparison with, with the actual mechanism. This is also important in order to understand, the kinematics of the collapse for the later reconstruction. So with this, I conclude the case study number 3. And let me conclude here with these conclusions. Regarding the seismic events in Albania, first of all, it is important to state that we had 2 seismic events within a short time frame, which did not allow for time for a proper survey and repair of the buildings. Regarding the restoration strategy, the original anti-seismic system in these buildings is mainly made of timber ties, placed every 1 or 1.5 meters. Most of these elements are partially degraded or completely degraded in these buildings. But since, as we saw, for example, in the Tower of Kuria, it proved successful, it is suggested that first of all to restore the original anti-seismic system, of course, where possible, because there are also technical difficulties, and then to propose new strengthening strategies. Regarding the existing damage, pre-existing cracks were present in all the case studies, which I discussed here, but also others which I did not tackle in this presentation, or joints or construction phases. And this weakness has proven to be, one of the main issues related to collapse or failure of these buildings. So they have to be, let's say, assessed with care, before or when possible, before the actual earthquake. Regards to the structural analysis, application of the structural analysis method have proven useful to understand the structural response and prove with scientific methods the causes of the failure, which is, in my opinion, very, very important, because then not to leave, space to, debate, but without some scientific proof. And with regards to the adequate and minimal strengthening, the use of structural analysis method helps to guarantee the accurate but also minimal technical intervention, which is a very important aspect in the restoration process. Finally, let me conclude here with an acknowledgement that for Cultural Heritage Without Border and the team, Leila, Nedi, Stavri, Anna, Anissa, and Yora, who were part of this amazing research. So thank you for your attention.
Thank you so much for that wonderful presentation, Grigor, and all the attention to the technical detail as well and the analysis techniques. I saw a comment as well in the chat about the diversity of the presentations. And indeed, it's something today that we really try to focus on. We have presentations from Anatolia, Nepal, Albania, India, and Peru. But we also wanted to ask you, we will have a follow-up webinar on this topic of traditional constructions and earthquakes. And so we wanted to ask you, what regions would you want to see represented in the follow-up seminar? Let us know in the chat. Even if you can present on it, send us an abstract. We will send out the call for presentations later. Then now we will move from the Balkan back east to India, where Arun Menon will give us the next presentation. Arun Menon is an associate professor of structural engineering at IIT Madras. He holds a degree in architecture, as well as a PhD in earthquake engineering from the University of Pavia, Italy. His research interests are in the structural aspects of historical constructions, the earthquake behavior of historical masonry structures, and the development of earthquake-resistant structural masonry. He has been involved in conservation projects in India, Bhutan, Myanmar, and the Philippines. Welcome, Arun.
Thank you. Thank you, Tim. Good day, good evening, good afternoon to all those who have joined into this, this fantastic ensemble of presentations from different parts of the world. I thank the organizers of ISCARSAH for this opportunity. And I wish to take you through some of the learning that I've had with my co-workers here in India and the neighboring countries. So the title of my presentation this evening is Seismic Resistant Traditional Construction Features and Structural Systems in the Indian Subcontinent. To begin with, just to give you an overview of seismic resistant traditional constructions in India, it's important to sort of understand the extent of seismicity, the regions of seismicity from the point of view of severity and the point of view of frequency of occurrence of earthquakes. And in that context, it's important to talk of the Alpine Himalayan belt, which has been a region of the development of a very large number of local seismic cultures, LSCs that we refer to today. This extends all the way from Myanmar to the Alps in southern Europe. So you have different forms of earthquake resistant traditional constructions that have developed over time, well documented, well understood, well researched in different parts of the country. And I think the efforts to protecting them is an area which requires focus. So as far as India is concerned, you have the interplate events, which is at the boundary of two tectonic plates, and that's the Himalayan region, and that's where you have the large earthquakes, and they're rather frequent as well in this region. So constructions such as the Dhaji Diwari construction in Kashmir, the Tak construction in Kashmir, the Katkuni construction in Himachal, which are all locations sitting along the plate boundary and therefore are subjected to interplate type of large frequent earthquakes. But you also have the Assam type of construction, which is again in the same region, closer to, in Assam and regions around Assam like Sikkim, called the Ekra construction. So these are part of the local seismic cultures in these regions. But you also have constructions which have shown to perform well during earthquakes, and that's with specific reference to what are called the poles or constructions in Gujarat. And this is a region which is very different in seismicity from the rest of the country because it's away from the plate boundary, and you have intraplate earthquakes here. These are large earthquakes, but not so frequent. In fact, the 1819 Bhuj earthquake in Gujarat was followed by the 2001 Bhuj earthquake, two large magnitude 8 earthquakes. So you have a difference in seismicity and therefore differences in the local seismic cultures as well. It is therefore interesting to look at, we always try to take lessons, learn from regions where there has been significant earthquake activity, learn lessons from important earthquakes, large earthquakes. Every earthquake has something to offer in the broad canvas of knowledge that develops over time. It's interesting to look at regions, particularly in a country like India, where you have regions of high seismicity and regions of such low seismicity that people have never heard of earthquakes in certain zones. So looking at, and we had this opportunity of studying some of the stone constructions, trabeate, post and lintel stone constructions in South India, which is the peninsular region of India, where earthquakes are almost unheard of. And we've not had important earthquake in at least 500 years. It's interesting to look at the hypostyle halls, multi-pillared stone constructions, and understand what gives them safety against earthquake forces, and how well would they perform in a surprise event, in a maximum considered earthquake, for example, for the region. So we were at a point in time examining the earthquake safety of such constructions. As you see, a 4-pillared construction and a 16-pillared construction, and examining this, considering that this is a low seismic zone, looking at the code-defined levels of earthquakes to even understand how would these perform compared to the prescribed levels in the seismic codes. And given that these are stone constructions, we're really looking at monolithic elements, beams and columns. And so limit analysis is something that gives us a good insight into the performance of these rigid blocks. It's interesting to note that these constructions have no interlocking between the monolithic elements. That is, they're devoid of any sort of positive connections. They do have a slight rough edge, and that is a marking of where they should be seated with each other. But this is more so for alignment purposes during construction and not to provide resistance to lateral actions. So you can assume that the positive interconnections are absent in these constructions. And it's actually interesting to note that some of these constructions can actually be vulnerable to levels of earthquake shaking, which South India has not experienced, as I said, for at least 500 years from the recorded history of earthquakes. So no positive connections between these posts and lintels, and these appear from limit analysis to be vulnerable to overturning effects. Of course, there is a certain role because of the frictional resistance that it depends on. There is a role of pre-compression, which is extremely critical. And that's the sort of understanding we would have. But then moving on to regions within India where there is significant earthquake activity, it's interesting to see the articulation of joints. And therefore, one starts understanding the necessity of those features in the construction and the importance of retaining them in the construction, in any reconstruction or any rehabilitation effort. The focus is particularly on articulation of joints. As I said, the absence of seismic resistant features is what made us look at the South Indian constructions in regions of low seismicity, what is expected to happen. However, you should also understand that the absence of seismic resistant features in constructions can be considered as an evidence of a region's seismicity level. And that is a sort of a confirmation of historical earthquake catalogs, if you want. But if you then look at regions of significant earthquake activity, parts of India and particularly looking at Nepal, and you see the incorporation of specific features such as tenon and mortise joints and shear interlocking, which is rather significant. These keys, shear keys that are rather significant in dimension, gives you an understanding of the role these play, the critical role that these play in protecting the construction. However, in this particular case, you do see collapse of structures despite having such features. And that is possibly due to two reasons. One, that the large amplitude of displacement is what is causing shearing off damage to stone shear keys, or in case of timber, deterioration of the timber would mean that it really does not have adequate interlocking in the event of an earthquake. Looking again at certain regions where earthquake activity is significant in India, looking at Gujarat, which I was mentioning a while ago as regards the Bhuj earthquake, we do see evidence of use of dowels in iron and dowels in wood. This is a picture of an archaeological monument, a part of an archaeological monument which underwent partial collapse in the 2001 Bhuj earthquake. But if one were to look at the construction of the walls of this minaret, you would see details of this nature where two blocks of the stone masonry, adjacent blocks of the stone masonry, are provided with interconnection with such depressions into which timber dowels could be, wood dowels could be embedded, but they sit embedded in line. However, what happens over time is that there is deterioration of the lime because of action of water, moisture. And once the lime is lost, you have the bare wooden dowel that is exposed to the elements. And over time, the wooden dowel completely disappears. And then you have just a pack of stones which are seated together without the deformation capacity that this sort of a detail was providing. So in the reconstruction efforts, particularly after an earthquake in historical monuments of this nature and the reconstruction efforts, it's very important to be able to identify the role of such interventions and replicate them or see if they're being replaced with something that it's conducive to the overall characteristic of the construction. If we were to examine higher seismic regions like Himachal Pradesh, which is again in the Himalayan range, Kangra, a region of a massive earthquake in 1905, you can see constructions make use of iron doubling. Of course, this is again from the point of view of providing deformation capacity, but corrosion in metal, unless it is protected, in some certain cases embedded in lead, but not in all cases, would then lead to damage in the stone itself. Moving on to the specific examples of the traditional constructions in the high seismic zones, the timber-laced masonry construction of the Tak in Kashmir is one of the most important, and it's categorized as timber-laced masonry, and you'll appreciate in a moment why it is a timber-laced construction system. If one were to examine the architectural typology in the construction, you would tend to think that this is a sort of a multi-story isolation system, because the Tak constructions of Kashmir are really constructions that are about 3 stories and 4 stories in height. So the Tak constructions would actually have a random rubble masonry foundation over which you would have a wooden plinth band. And this is sort of a runner that will go all around, sitting at the two edges of the masonry wall, the stone masonry, random rubble masonry plinth. And then the brick construction commences atop these timber bands. Now, what is interesting is the construction makes use of a floor band and a ceiling band, and has the floor joist actually supported between these 2 bands. So as you can see, you have a floor band, you have a ceiling band, and you have a floor band, and the timber joist, which is actually supporting the floor, is constructed on the joist, but the joist is embedded between the ceiling band and the floor band. So you can see how the load transfer is actually happening directly to the timber system in the floor, and the walls are interrupted by these by the lacing in timber. So this goes on for several floors, and then you have a roof system which is again in timber, supported on the load-bearing masonry walls in a similar manner. So you could actually look at this as a sort of a multi-story isolation system, but one has to remember that with the timber and the load-bearing masonry construction, deformation under gravity of the timber occurs. So sliding is not something that is permissible, that doesn't really happen, but still you have a deformable timber layer which is sandwiched between masonry layers, and sort of a sub-paneling that is allowing for reducing the brittle behavior of masonry stories. So that's the elevation of a Tak construction, an example from Srinagar called the Fateh Kadal School. Coming to the Ekra construction, you can actually see this sort of a lightweight timber-framed sub-panel construction system called the Ekra. Ekra really comes from, it's the name of the grass, the Ravenna grass or the elephant grass, which is actually used to create panels. And these panels are at times packed with, externally packed with mud or with lime to make it durable, and to also provide environmental protection from the cold weather. This is found in areas of Assam, high seismic zone, Sikkim, a high seismic zone. And so you have a lightweight construction, and you have sub-paneling with the timber, and you have a lightweight roof. So you have a very interesting system that is highly resilient to earthquake action. Problems with such constructions, the foundation systems typically sitting on hilly slopes, you have the random rubble foundation or the random rubble plinth. And this is an area which often gets damaged, and resetting of the entire construction is possible because the superstructure almost completely survives the earthquake. The plinth needs to be reconstructed, and the superstructure can actually be reset. So you see examples here where the damage is limited to the random rubble plinth or the random rubble foundation, and the structure sort of survives. This is another example of a school building with this sort of a construction, lightweight, sub-panel, timber-framed, excellent in its performance under the earthquake. But then you, as I said, you might have, because of the damage to the foundation, movement of the structure. And this movement of the structure, you see the tilting of the building here, without even dismantling the entire building, masons put the building back into a vertical position. Coming on to a region, again, which I mentioned earlier, Gujarat, where the frequency of earthquakes frequency of big earthquakes is close to 180 to 200 years. And therefore, there's always a question whether the traditional constructions there really are designed or deemed to be earthquake resistant because of the observations of good performance in the recent earthquakes. So we're looking at the poles of Gujarat. Ahmedabad has a large number of them, and Ahmedabad has been declared as a World Heritage City now. So you have, as I said, the difference between the type of earthquakes in the region of Gujarat versus those of the Himalayan area, the intraplate earthquakes in Gujarat versus the interplate earthquakes of higher frequency in the Himalayas. So this typology has received certain attention in the recent years on their good performance in the 2001 Bhuj earthquake. I'm making particular reference to two studies here, one in 2006 and one much more recent in 2020 by Satvika Pancholi from CEPT University. And the intent was to understand when you don't have a very formal system following a local seismic culture, which is not very evident in the construction, what is that is leading to good earthquake performance. And in that context, her study identified that it is really the shear wall area, the shear walls and the area of the shear walls in the orthogonal directions, the orthogonal connections that are introduced, though not very systematically, but they are present, the regularity in height, again, we're talking of multi-story constructions, and the state of conservation. The state of conservation plays a very significant role. In today's context, this being a World Heritage Site with a number of these structures within the historic city, the question is, these are residences, and how is it that, how is the local population able to retain these structures and despite an urge to make modifications or convert them into newer facilities. This example here itself, you could see that there's a floor and reinforced concrete added above the original structure, or it might have been a replacement of a portion of the structure with a new construction. So here is a category which performs well under certain conditions under earthquakes, because you don't see a formal earthquake resisting system systematically present in all the examples that are remaining. But their good behavior in the earthquake can actually be attributed to a few geometrical and material related features, and therefore they need to be addressed in any rehabilitation or renovation effort. So that brings me to my concluding slide and sort of piecing together all that I've been talking about. While we are talking of the earthquake effects on such buildings and their resilience to earthquakes, we must also remember that we are sitting in multi-hazard scenarios in many cases. The example that I'm showing you here is of the Wangdi Phodrong Dzong in Bhutan, which is of course affected by earthquakes, is also affected by landslides because of the setting of the structure, but was severely damaged and partially collapsed because of a fire. So this sensitivity to multiple hazards is important. What may be good for one may actually be counterproductive for another hazard, and timber framing or timber elements in masonry is a challenge from this perspective. But one must also appreciate the fact that it is not heritage professionals or people working on the preservation of monuments who mostly live in these constructions. And therefore, incorporation of new facilities, providing new services, new aspirations, changed lifestyles are aspects that we really have to address. Of course, if it is a historical monument and a protected monument, it's a different matter. But when you're talking of heritage structures, widespread examples of heritage structures, we really must be attentive to the fact that new directions in terms of the facility with services is a reality, and how does one address that? It is in this context that one needs to identify critical parameters that guarantee inherent earthquake resistance, as we saw in the previous case of the pole constructions. We also, in certain cases, might have to incorporate earthquake resistant measures where deemed necessary. Timber, for example, availability of timber is a problem in many places today. And there's also legislation in hilly areas that you cannot use timber, but one has to really look at the fact that timber is a renewable resource, and this is feasible. So again, looking at the reconstruction happening at Wangdi Phodrong Zong, and incorporation of certain seismic improvement measures with reinforced concrete through stones is a fantastic example of trying to improve aspects of the structure which might have poor seismic performance. The same with the Chasilin Mandap in Bhaktapur, which collapsed in the 1934 earthquake, was reconstructed with certain features incorporated, and survived the 2015 earthquake. I leave it here. Thank you.
Thank you so much for that wonderful presentation, Arun. From India, we will move back west all the way to Peru. It is, for our last presenter, it's a great pleasure to welcome Claudia Cancino. Claudia works at the Getty Conservation Institute as a senior project specialist. She graduated in architecture and urban planning from the University Ricardo Palma in Lima, Peru, and earned a certificate in conservation at ICROM in Rome. She also holds a degree in business administration from ESAN in Lima and received a Master of Science in Historic Preservation with an advanced certificate in conservation from the University of Pennsylvania. Currently, she manages the Urban Architecture Initiative, which includes the Seismic Retrofitting Project, the Urban Architecture course in Al Ain, Abu Dhabi, and the Terra 2022 Congress in Santa Fe, New Mexico. She also manages the retrofitting component of the GCI project in Bagan that focuses on the conservation there. Welcome, Claudia.
Thank you, Tim. Good morning, good afternoon, and good night to everybody. My presentation is going to try to shortly describe, hopefully in 15 minutes, how local knowledge over centuries has helped the design of traditional retrofitting techniques for earthen buildings in the Peruvian Andes. I will use at some points some of the research, testing, and implementation project developed as part of the seismic retrofitting project to explain the efficacy of these ancient techniques. Earth construction is based on the use of a very basic material, the soil, which combined with the right amount of water and compressed air form the material base to produce a variety of techniques that were developed by humans through time. These techniques, pictured here from left to right, ram earth, mud bricks, or adobe in the Middle East and South America, cove, wattle and dog, among others, were the results of our ancestors' numerous tries and errors, making great use of their natural resources. I don't know why it's not, okay. Being the soil such an important element for earth construction, I have placed here a definition given by Jean-Marie Teutonico in 1988. I would like us to concentrate on the fact that the types, the relative proportion of these particles, and the forces between them give the soil a particular character and behavior. Hubin and Guillaume defined in 1994 this clay schematic structure and identify also three main clay minerals that define the behavior of a soil. These clay minerals are from the most stable to the most unstable one, kylonite, alite, and monorelite. Their stability in contact with water and air depends on the strength between intermolecular ionic or covalent bonds, which varies dependent of each type. These clay materials that are part of the clay particles interact with water at the molecular level in many different ways. In molecular physics, the van der Waals forces are distance-dependent interactions between atoms and molecules. These forces are present, for example, between molecules of water. Unlike ionic or covalent bonds between, for example, aluminum and silica layers seen in the previous slides, these forces are not a result of any chemical electronic bond, and they are comparatively weaker and more susceptible to being disturbed. The van der Waals forces that attracts water molecules among themselves are the same forces that allow the different clay materials to break, separate, stay in dispersion, and reconnect. These forces, therefore, also allow to create different states of soil suitable for different construction techniques. Water, despite being portrayed as the enemy of earth construction, it actually contributed enormously to its creation. For me, it is amazing that human beings went from playing around with these scientific principles to create a series of techniques that build impressive dwellings that are now World Heritage Sites and have survived over thousands of years. They are, for me, also a testament of how ingenious human beings are. The development of different earthen construction techniques around the world are basically based on the principles explained before. As you all recognize, this is a map that shows the seismic hazards around the world, and I have overlapped the regions populated with earthen sites. Peru is located in a seismic area and has suffered earthquakes since the pre-Hispanic period. However, this situation has also supported the improvement of the local building culture to adapt to its environment and create original retrofitting techniques that are still in use in Peru. Peru has a variety of buildings made with a series of earthen techniques that has evolved through time with the intention of standing against seismic forces. There is evidence of potential seismic isolation at the archaeological site of Caral, constructed around 3100 before our era. Caral is considered one of the earliest urban settlements in the Americas and was built in stone and earth. Recently, engineers from the Pontificia Universidad Católica del Perú has researched a base simulation technique found in this ancient site, which apparently stopped the out-of-plane collapse of exterior adobe walls. The use of the chicras, a vegetable fabric bag with gravel stones inside, apparently dissipate the energy of seismic events. This is an early demonstration of how ancient Peruvians made good use of available materials to adapt to earthquake for centuries. You can find further results of the test run at PUCP in several international publications, but in generally, it has been proved that the chicras actually help to dissipate the seismic energy and preserve these ancient sites. Archaeologists have also discovered some early evidence of wattle and dog panels in Caral, as seen in the images on the left of the slide. This technique, that we call quincha in Peru, was apparently later used to build residential dwellings in northern Peru, as shown by the hypothetical drawing of the house of the Lambayeque culture on your right. I am not sure if the use of different materials as part of an isolation technique was also applicable for the construction of the famous Peruvian Andes, which flourished during the Inca period from the 12th to the 15th century of our era. I guess further investigation should be done, particularly if you consider that one of the most significant sites in the seismic region was constructed with unreinforced stone masonry over a series of man-made andenes and is still in place. Several archaeologists have also noticed the use of reinforcements at the end of the wooden elements of hypothetical roofs at the dwellings at Machu Picchu. This tradition of tying the ends of the wooden beams to the masonry walls was later used for the construction of roofs during the Spanish viceroyalty. However, many centuries before the construction of Machu Picchu, the coast of Peru was full of a series of large earthen complexes built either in adobe, like the Huacahuantillo in Lima, or ram earth or tapial, as we call it, like the site of Cajamarquilla. The Spanish arrived in 1532, and in 1536, there was a document called the Real Provision that ordered the construction of good houses for the Indian population of the Viceroyalty of Peru. The Regulation of Madrid, published in 1565, stipulated that structural walls in houses have to be built in ram earth or tapial, a construction already used in the Iberian Peninsula. Harterreg, a well-known architectural historian, has documented the construction of some houses with tapial in the 16th century in Lima. However, the majority of buildings and churches were constructed in brick and stone during this period. Several documented earthquakes, as the one that you see here in the paintings, during the Viceroyalty period, shaped and modified these construction techniques to make them more seismically resistant. The first documented earthquake happened in October of 1606, and it apparently damaged several buildings in Lima. A second earthquake, later in 1609, made the municipality of Lima, at the time Cabildo of Lima, made it suggest to reduce the height of the buildings and to study traditional construction techniques already developed by the Indians, like the quincha and the adobe. In 1681, there were several earthquakes, and particularly the one that happened in October 20, pushed the Archbishop of Lima to write to the King of Spain, suggesting the construction of only one-story buildings, avoiding second-story houses in Lima. The Viceroy Conde de la Moncloa ended up being the person in charge of the reconstruction of the city of Lima after this earthquake. And finally, he disposed that if upper stories were needed to be constructed, they should be built with quincha. So as the drawing on your left shows, typical dwellings in Lima were built with adobe in the first floor and quincha in the second floor after the 1681 earthquake. Later, the technique were modified, and I want to mention here that this technique is very similar to some techniques that Gorun has shown you as in Anatolia, as well as Arun has shown us the ECRA system in India. So for me, it's still impressive that in different parts of the world, you can find similar construction techniques. They were changed over time, as I said. For example, the panels in the second floor had adobe fillings in the lower part of the panel, and we call this section citeras. Then they did this probably to better connect the panels with the wall below, while the third floor in some cases had wooden diagonal posts at the corners to probably avoid overturning. As part of the Getty seismic retrofitting project in Peru, the Pontificia Universidad Católica tested a replica of both types of quincha for the first and the second floor, and an additional historic panel demonstrating their flexibility. The results were published and can be downloaded as part of the publication that you can see on the right. Probably after the dome of the Church of Santo Domingo in Lima, that you can see here on the right side of your slide, and was originally built by Fray Diego Matamoros in wood, cane, and lime, a few years before the earthquake, survived the 1681 earthquake. It was probably because of this that the recommendation that Conde de la Moncloa gave, the churches had to be built with lighter domes and vaults. There is a theory that Europeans borrow the wooden construction techniques used for ships, as you can see on the upper part of the left images of the slide, to design lighter vaults and domes. So it is unclear if the techniques used to build these vaults and domes in a lighter way, was brought from the Iberian Peninsula, was designed in Peru, or it was a combination of both. It seems it was after the Dome of Santo Domingo was constructed and survived an earthquake that the famous roofs of the San Francisco convent in Lima were constructed. Nowadays, all the Viceroyalty churches of the coast of Peru are built with this system, including the construction of wooden columns and pillars like the ones found at Ica Cathedral, as well as the Cathedral of Lima. In 1746, there was another earthquake with its epicenter in Lima around 3,000 and around 3,000 churches and houses collapsed. After the earthquakes, the viceroy Jose Manso de la Moncloa, better known as Conde de Superunda, that you can see here in the picture, asked a mathematician, Luis Godin, to carry out a damage assessment and provide technical recommendations to improve the structural behavior of the existing structures. So Godin, in an official document, suggested to the Cabildo the mandatory use of earth, cane, and adobe instead of lime, brick, and stone as construction materials, the use of quincha for wall partitions, and the use of quincha wall for the constructions of the second and third stories of residential buildings. Godin also suggested the increase of the width of adobe walls, and finally, the construction of buttresses against church adobe walls. The buttresses have proved to be a very efficient retrofitting solution, stopping particularly the overturning of walls, and can be seen in most of the earthen churches in the Andes, but also in some of the rural churches of the coast of Peru. At some point, the arch that normally divides the nave from the altar of these churches was changed from stone to quincha as well. However, I have not been able to find exactly after which earthquake this tradition was changed. As you can see, the tradition of building with earth have continued over centuries in Peru. And it's still very much in use. And now not only masons are training the job, but also the teaching of earthen construction and conservation is part of the curricula of architecture and engineering schools. This has been, of course, an advantage for the conservation of earthen sites. There is a lot of experience implementing conservation projects in Peru, taking into consideration the seismically resistant and/or retrofitting techniques developed through time. You can see in the video the reconstruction of the Quincha Arch, for example, at the Church of Puñotambo, an SRP implementation project in Cusco, as well as the installation of the traditional wooden tie beams. Nevertheless, it will be important to mention that the use of key tie connections from outside found in the Inca dwellings in Machu Picchu have always been used, but the quality of the techniques have changed over time. A very detailed design of the key tie connections was developed as part of the implementation project at Puñotambo. The Pontificia Universidad Católica also ran a series of tests to understand the performance of tie beams on these type of churches. The installation of wooden corner keys to avoid seismic damage at wall intersections appeared at some point during the Republican period. The use of these retrofitting techniques within a conservation project started formally probably during the 70s. And I was also surprised that this type of corner keys were also presented by Grigor in previous presentations. For the Church of Puñotambo, a series of wooden corner keys and collar beams were designed, modeled, and implemented based on the construction expertise of our Peruvian colleagues. The study of the material and structural characterization, as well as the modeling of these techniques, have been published as part of the SRP and can be downloaded from the Getty website. Similarly, the retrofitting proposal for 2 historic earthen sites in Peru are presented there, so you can see more detail the development of the conservation project. I have mentioned that the Pontificia Universidad Católica de Peru has worked with us as part of this project, but I would also like to mention that the University of Minho in Portugal have developed the modelings, and we have worked in close collaboration with the Ministry of Culture in Peru. It is very difficult to tell a linear story that explains the development of seismically resistant construction techniques in Peru. I will say it has always been a combination of local knowledge, professional expertise, and trial and errors after earthquakes. Nowadays, Peruvian colleagues keep working in the further development of building norms and codes to better preserve these magnificent earthen sites. So thank you so much for all your attention, and I hope you find this presentation interesting. Thank you.
Thank you so much for that wonderful presentation, Claudia. As we've had our webinar for already 2 hours, I think we will take a few of the questions that were submitted. Unfortunately, we will not have time to answer all of them. I suggest we continue the discussion for about another 20 minutes for the people who can stay. So I am hoping that all the panelists and presenters could turn on their video, and then I will cycle through a set of questions. And this first one I would like to throw to all panelists because I think it concerns a problem that all of us deal with. And it was raised by Pierre Smars from Taiwan, well, originally from Belgium, just like me. So Pierre says, related to Kathmandu, the temple, but I think we can relate it to other places as well, was not maintenance the main problem? I imagine that there were quite a few strong earthquakes before. Ancient technology may not be perfect, but if it resisted a few earthquakes, it may not be that bad. I think Pierre makes a very valid point here that maintenance is important. And in a way, we can think of buildings in an analogy with patients seeing a doctor. And so we could think of an earthquake as a heart attack. And so if a patient comes to see his doctor and says, hey, I've had 5 heart attacks, the first thing we don't say is, okay, you've survived 5, you're fine. We wonder, like, will the next earthquake kill him? Will the next heart attack kill him? So what do you think about this, this aspect of traditional construction having proven itself on the one hand, but on the other hand, having these maintenance issues and this constant threat due to earthquakes? Who wants to take a stab at that of our panelists?
Well, I can start since it's was sort of in connection with the Kastamandap. Of course, our big question was that the Kastamandap didn't collapse during the 1934 earthquake, and sort of why didn't it collapse? Did we really understand the structure properly? And I think that really trying to understand the traditional structures and technology is something that we really need to work on. And I think it's also a question of language. We had, the artisans on the one side and sort of the experts and engineers on the other side, and trying to come to a sort of a language that both of them could discuss in was not very easy. So I think it is, sort of still a lack of a sufficient understanding as on the one side. The other is we saw that clearly that there was a lack of maintenance, especially after it became a monument, which means before there were people living in there, people using the monument. And in 1966, when the monument was sort of restored and looked at as a national monument, the people were kicked out. And so you can see that, sort of that lack of sort of daily use of a monument was also probably one of the reasons why there was less maintenance and monitoring, sort of this daily monitoring. I think it all comes together. And now the third component is we'd love to make it stronger and better. The question is, what does that mean? And there's, we saw that after the Gorkha earthquake, that a lot of monuments that collapsed were due to sort of inappropriate intervention. So if we're going to introduce something new into this old system, we better really understand its impact. And I think that is, again, something that we really need to work on. We didn't do a good job in the past, and we really have to do more research on that. Thank you.
Tim, I would like to add to what Kai was saying, that the project at Getty started really after the 2007 earthquake in Peru, and we did a preliminary study of the damage that some of the historic sites suffer after this earthquake. And I should say that the general conclusion was that really lack of maintenance was a big detriment on the, damage of the sites during the earthquake, either interventions with new materials without, any previous research, like cement, renderings over the bolts and domes of these quincha roofs at the churches, or the decay of the wooden elements that were not working anymore. So I think maintenance plays a really big part on the efficacy of these traditional retrofitting techniques.
Thank you, both Kai and Claudia, for those insightful answers. I would like to take the next question from Poonam Mascarejas, and she directs it to Kai and Professor Arun. So we'll give it to Goran Arun. And so the question is, can the reconstruction, like in Kathmandu, be informed of traditional sound practices such as those from Anatolia? What would be the cultural implications for the resident community? Can ISCARSAH promote a build back better using traditional systems, but not necessarily from the region itself, but from the international repertoire within the material typologies? You are muted, Goran.
I didn't understand the question, really.
So the question is whether we should be taking, for example, reinforcing techniques that have been tested and proven in Anatolia, but might not be part of the traditional repertoire somewhere else, like in Peru or Kathmandu, and whether ISCARSAH would promote a build back better based on techniques from another place that are traditional, introducing them to another area in the world.
I'm not sure if it is necessary, because each culture have its own traditional methods. Maybe it's not researched very nicely, but I'm sure each country have their own special traditional techniques.
Thank you. The next question is again for Kai, and it was from Eugenie Crete. She was saying, if I understood well, you did not follow the outcomes of the initial structural assessment because of local actors being attached to rebuild the same way. Wasn't it a very good opportunity to understand deeper the original seismic design and not implement these, quote, reinforcement strategies? There are a lot of examples of this kind of reinforcement that turned out counterproductive. So what is your opinion about the initial structure assessment outcomes compared to what was actually done? And do you have more info to share about the works that were done in 1966, 1972, and 1984? So Kai, could you comment a little bit more about that initial assessment, and then what was done and what was not done and why?
Yeah, of course, the initial assessment was sort of a standard procedure, which then was not accepted by, well, quite a lot of people who were, trying to get the monument rebuilt in a more traditional manner. So again, it's sort of this dialogue between do we introduce sort of, so to say, foreign materials and technology knowledge into these traditional structures or not? I think that's an ongoing discussion, but in this case, there was really, the community got together and said, no, we want it rebuilt as it was. Now, the problem is, what does that mean, as it was? Because once it's collapsed, we needed to sort of look at, the different elements and sort of reconstruct or redesign the monument. We had some rough overall plans that were sort of measured on, but not all the details. So whatever elements were found, it had to be sort of reinterpreted based on traditional knowledge and sort of methods. And really one of the only things that well, with the reinterpretation, that was a process in itself. But then the part that really was discussed, especially together with the structural engineers, was in connection with the brick masonry, because this was one of the earliest structures. So it didn't even have the timber lacing, which later construction, this timber lacing was introduced all over Kathmandu. Now, the point was, do we use this later introduced technology, which is local in the structure, which would have, not had it, or for some reason it hadn't been introduced. Now, there's a lot of questions that arose. We tried to reinterpret it in a manner that was sort of acceptable to everyone. And also, of course, working very closely with the local artisans. I mean, I think they were very much involved in the decision-making process. So yes, not everything is perfect. You cannot, there are many questions that arose. But I think, it sort of sets the stage for further research. And yes, I have much more information. We're putting together a publication, and hopefully by, within the next few months, there'll be something specific on this.
Great, thank you so much, Kai. We look forward to that presentation. Publication.
So Tim, I hope you don't mind, but I would like to add, just to reinforce what Kai is saying regarding how important is the interaction between the academia and the traditional craftsmen and traditional knowledge. After the 1940 earthquake in Peru, there was a strong sort of push to stop earthen construction in Peru. The interventions on historic buildings were basically made in concrete, but then it was the academia, the engineers at that time from the Pontificia Universidad Católica del Perú and another university, the Universidad Nacional de Ingeniería, that actually got into this and tried to develop some research in collaboration with traditional masons. So it's always good to have both both sectors working together, because you have the local knowledge, but also you can support that local knowledge with scientific research.
Thank you, Claudia. I think that's a very, very valid point. I'd like to give the next question to Grigor. The question is from Rafael Discipulo, and he's asking whether during the last Tower C restoration, if you considered inserting tension ties. And I also wanted to add immediately a second question from Arcadius, who asks whether effective repair or protection solutions for the massive cracked structures against earthquakes and aftershocks have been considered. So I think those two are kind of linked. I was wondering if you could comment on that, please.
Yes, thanks for the question. Well, I think that in the case of the Tower C, there has been in one part of the tower, in the later stages, there has been the presence of timber ties. Now, the project will be finalized now shortly, but we are considering inserting these timber ties in the structure. It is difficult, but at least we would like to insert at least the external one, because we have in each level, you have usually 3 to 4 timber ties, but at least the 2 external ones probably could be inserted. So we are looking at this possibility, and I think it's useless. It's useful, sorry, because it restores the original type of structure. Now we do not have the timber ties because we just see the voids because they are degraded. Well, then, with regards to the effective repair techniques, the solution on such massive structures, I think that the application of modern methods, gives us the possibility to see, let's say, the weakness of the original construction technique, how it actually performed, and make a comparison with what we saw on site, and try to make, let's say, the improvements, and actually test these improvements virtually before we can actually apply them on site. So I see that there is a possibility here, using simulation models, to actually have effective repair solution for this structure. So there is an advantage from technology, and we should use it. That's my conclusion to this.
Thank you, Grigor. And I think that's a great point. And I think also when we saw Claudia's presentation, we saw clearly how traditional techniques were studied first, and then extensive modeling and research was done to actually virtually test if they work. And I even believe that, Claudia, in this project, the plan is also to monitor, even after implementation, that the techniques work as expected and as modeled. Could you comment a little bit on that, please?
Yes. I mean, we're really happy about this because, first of all, the engineers from the University of Minho were able to go back to the church once the church was finished and all was implemented. And they actually, did some sonic and dynamic testing to recreate a model once the techniques have been implemented. And the results were that the techniques were actually working as originally planned. And then what we are going to be doing in the next couple of years, after this pandemic, is we're going to install some monitoring equipment that's going to allow us to give us a better idea of how the building perform on the next 5 years. I mean, it's a big investment for this church, but I think we can also use the equipment also to monitor other buildings that we plan to implement. But the results, I think, of this, immediately after implementation, modeling, as well as the structural monitoring over a period of at least 5 years, is going to be published as well. So yeah, I think we're very happy that we're going to be able to do that.
Thank you, Claudia. Being mindful of the time here, and that we're already going 20 minutes over our scheduled time frame, I would like to invite the panelists to make final comments, if they have any, if they've seen a question or have seen similarities that they would like to address to finish up. So any general last remarks?
May I?
Of course.
Tim, Arun here. Very quick comment to just wrap up. That interesting discussion on whether a technique for retrofitting adopted in a certain region is applicable in another. I think that requires a certain amount of application, because the laws of physics do not change from place to place. I think once we understand the materials may differ, the climatic conditions may differ, the construction systems may differ. But once we are able to characterize that, laws of physics are the same everywhere. So I think there's a lot of inspiration that we can draw from an understanding and incorporation of a certain technique in another place. And I think there's abundance of knowledge that we can all feed into and learn from as examples. Thanks.
Thank you.
Just a very short comment. I think we need much more research to really understand these traditional structures, and we should not jump to, introducing sort of other technology into these structures. And just looking at the situation in Kathmandu, even before the earthquake, but also with the work going on afterwards, I think there was really a lack of research. The reconstruction, well, they jumped into it with some changes, interventions, and it's always the build back better means you introduce new technology. And I don't think Build Back Better should mean that. I think we really need to work on understanding the traditional technology. And yes, we might need to improve things, but then with the detailed understanding of the traditional structure, and not just, putting in new things. And I think, the research is still lacking. We need to work on that. Thanks.
I think
I'd also like to add, and I join Kai in this respect. And I always advise to work with history of architects because they study such traditional techniques, but they don't know much about the structure. If you work together, then you can interpret what they get. Also with the archaeologists, it's very hard to work with archaeologists because they don't like to share, but you can get, if you insist so much, if you say that your perspective is different, but working with different disciplines is very important.
Thank you. And with that call for a multidisciplinary study of more traditional construction, I think we can end the seminar. Thank you all participants for attending, for asking insightful questions and actively participating in the chat. We look forward to seeing all of you in the follow-up webinar. We will send out a call for presentations. I saw a long list of interesting places that we would want to hear from next. So with that, thank you. Thanks to all of you once more. Thank you to all the speakers, and hope to see you in our next webinar.
Thank you. Thank you very much.
Thank you.
Thank you. So thanks to you, team, for the moderation.